Alrighty. Hello, everybody. Welcome to another session of Simon Says. Today, I'm going to be continuing with our elements of creation, looking specifically at light, all the weird and wonderful things to do with light. So let's dive right in. So first, we're going to have a look at light in Scripture and what God says about it. Then we'll start with the nuts and bolts of what exactly is light in the first place. Then we're going to have a look at its importance to humans, and then zoom out a bit more to its importance in nature. So God describes himself as a God of light in Scripture. Not only that, it's the first thing he created. In Genesis 1:3, God said, "Let there be light," and there was light. And God saw the light was good, and he separated the light from the darkness. So on day one, he took a whole day to create light, whereas on day 5 or 6, he created who knows how many species. And so that gives us a tip that light is important, and probably complex as well. And not only that, but God, he identifies himself with light. In Psalm 104, it says he wraps himself in light as a garment as he stretches out the heavens and lays the beams in his upper chambers and their waters. So he took a whole day to make it. He associates himself with it, so there's probably some importance there as well. So let's have a look at what it is. And so physicists in particular are interested in its range of different properties, but we can define it as an electromagnetic wave, which is produced by an oscillating electric charge that produces mutually perpendicular oscillating electric fields and magnetic fields. That's a bunch of words salad. What it means is this. This picture shows what it's describing there. So what it means is that as a wave travels, so in this case from the top left to the bottom right, the direction of those green arrows. As it moves in that direction, there's oscillation of energy along the way. And so there's a vertical one there, the up and down of an electric field, which goes with a positive amplitude, then a negative amplitude. And then perpendicular to that, so at a right angle in that dimension, there's then a magnetic field which oscillates to the left and right. It's a very unusual structure, but it's all about a propagation of energy in a direction with both electric and magnetic fields, which are perpendicular to each other. So that's what it looks like as it travels. But it also travels in little individual packets called photons. And so it's possible to get to a point where you can't make light any smaller. We tend to think of it as a continuous stream, like we're turning on a torch. It just kind of streams and then it stops like a liquid, but it's actually made up of lots and lots of tiny little photons, and those photons can't be broken down into smaller packets as far as we're aware. And so light is also part of the electromagnetic radiation spectrum. And so what we think of as light is the visible spectrum, which is this teeny tiny section in the middle between about 400 nanometers and 700 nanometers. And so each color has its own specific wavelength. That's what dictates its color in terms of what we see as humans. But as you go higher or lower on the electromagnetic spectrum, you get different types of radiation. So at the lower energetic end, you get UV rays, X-rays, and radiation, gamma rays. So they're the dangerous ones. Whereas the longer wavelengths with less energy, you get your infrared, radio, microwaves, TV, all that kind of stuff there. But smack bang in the middle just about is that visible spectrum, and that's what we think of as light. All right, so us as physicists, we've been very interested in light over centuries for many reasons, because basically physicists spend a lot of time arguing about whether light is a particle or whether light is a wave. Is it a physical object thing, or is it a wave like I described before in terms of energy propagating through, not even through the air, it can propagate through a vacuum as well. And so physicists argued about this for centuries. And so in 1923, Arthur Holly Compton finally demonstrated that it shows particle-like properties when he took electromagnetic radiation, in this case X-rays, but we know that light is made of the same stuff. He took those X-rays and crashed them into electrons in different atoms, and it caused both of them to scatter. Not only did they scatter, they did so in a predictable way, which can be calculated using the laws of momentum. So I've got a little graphic here. So we've got a little X-ray photon. It could also be light as well, but it crashes into an electron and it causes the electron to bounce off this way. And then the scattered photon bounces off in a different direction. And so it needs to be a physical object for it to crash into things and to cause them to move. And not only that, but we can actually predict and measure the ways in which they move, and it's consistent with what we'd expect based on the laws of momentum. And so with this experiment, Compton was able to show that light is in fact a particle. It's a physical object which can crash into things and exert a force on them. So Team Particle was excited. However, thinking of light as a wave, even earlier than this, Thomas Young in 1801, he showed that light undergoes diffraction and constructive interference, and these are properties that are specific only to waves. And so even going way back further, he showed that light was a wave. They thought they'd call light as being a wave, but we now know that it actually shows properties of both, which doesn't make sense. How can it be a thing and not be a thing? But it is, because it's that amazing. And so Young's experiment, he used two slits and shone a light source through those two slits, and he was able to demonstrate interference patterns as a result of these. And so at the bottom there, we can see the light source coming towards some sort of barrier, black barrier there, and there are two slits in that barrier at the bottom. And so as as a wave passes through a slit, it will undergo what's diffraction, which causes a pattern of its radiation as it moves through that smaller opening. And so we can see two diffraction patterns, those semicircles going out, and they're overlapping, one for each of those slits. And so as a result of this, the light basically interferes with the light coming through the other slit. We have what's called constructive or destructive interference. Basically, it causes areas of higher intensity and areas of lower intensity. And so by the time that light hit a detector or the wall where you could see it, we saw this real clear pattern of areas of higher intensity and lower intensity, when otherwise you would just expect the light to pass through and just be there at the other end. And so the fact that we see these patterns when light interferes with itself was clear evidence that it is in fact a wave, as well as being a physical particle which can crash into things. So light is very unusual in that regard, and we call this the wave-particle duality. And so in the end, why not both? Well, it is. Cool. Moving on. And so light has some other interesting properties as well. So light is very, very fast. In a vacuum, it travels at 299,792,458 meters per second. That's about 1 billion kilometers an hour. Whereas the speed of sound, Mach 1, when you break the sound barrier, that's 1 million times slower at 343 meters per second. Light is very fast, and it always travels at that speed, as we've touched on before in previous videos. And so it's, even if you were driving a very fast machine and then launched light from that fast machine, it still travels at the same speed. It's weird like that. It can be affected by gravity and can be sucked into a black hole. That's why black holes are hard to see, because they don't emit light for us to look at. And light can also be refracted, which is science talk for bending it, which is results in some interesting things we can do with it too. And so this is an example of gravitational lensing. And so this is light being bent by gravity. And so we've got a large object in the middle, yellow there. I think it must be a star or a galaxy. And around that, we have this smear of the bluey white going all the way around that yellow. And that's actually one single object. We're actually seeing that object from multiple angles because of gravitational lensing. The light is actually being bent by gravity. And so that object behind this massive object is being bent by the gravity. And then by the time the vision reaches us, it's bent out of shape and we can see it from all different angles. And so light can be bent, and that allows us to see strange things. But it also allows us to see pretty things like a rainbow. And so when we're seeing a rainbow, it's because sunlight is passing through raindrops. And at the top there, it undergoes refraction, which breaks the white light, which has all of the colors of the rainbow in it. It breaks them down into all the different colors of light because they travel at different speeds when they refract. Then they reflect and come back to us, and we see them as a rainbow. And so this is the reason that the sun will always be behind you when you see a rainbow, because the sun has to come from that way and then do a U-turn and come back for it to refract in the right way and shape for us to see that rainbow. So always remember to have the sun behind you when it's raining, and you're going to see more rainbows. Alrighty, so light is interesting, lots of strange properties that make it really interesting, but also really helpful. And so as humans, we need light to survive and thrive as well. And in Matthew, it even says that we are the light of the world. We're called to be salt and light in the world. So not only does God associate light with himself, but us as his children, we can be associated with light as well. And interestingly enough, humans need light. We need it to see. We need it for our health in terms of producing vitamin D. And it also helps to regulate our regular patterns with our circadian rhythms. And so in terms of sight, this is a brief rundown of how we see. And so for us to see something, we need to have light enter our eye and light that's been directed there from the object that we're seeing. And so if I've got a green peg here, it's nice and green. What that means is some sort of light has encountered this peg and it's reflected green light, and then that green light's gone into my eyeball for me to see. And so I'm under white light here, which shines all different colors of the rainbow. And so if I have a green peg, what it means is that it's absorbing all the different colors. It's absorbing the blue, it's absorbing the red, and it's only reflecting the greens for me to see. And so that light must be focused through my lens at the front of the eye, and the iris opens and shuts more or less to control the amount of light, just to make sure that it's always optimal. And then as individual photons of light come through, those little specific little packets, they then encounter the receptors at the back of our eye, where these electrical signals are interpreted by our brain. And so the light that enters our eyes and is focused on our receptors is actually upside down. And the vision coming into our eyes is upside down, but our brain then flips it and interprets that to make it the right way up, which is really cool. And I think I heard about an experiment where if you wear glasses that flip your sight, your brain will flip your sight, but it'll go back after a while. I'm not sure about that one. But yeah, but the vision we do see regularly is upside down, strangely enough. And so at the back of the eye, after it's been focused and that amount of light is controlled, it hits these photoreceptors. You may have heard of cone and rod cells, so named for their shape. And they're the things that kind of actually pick up that signal of light. And so cone photoreceptors, we have about 6 million of those. They see one color each. So you have all a range of different cones, and when combined, they allow us to see the colors. And so if I'm looking at a yellow banana, it means that both the red and the green photoreceptors have been stimulated, and then we perceive that as yellow. So I know that it's messing with the art people out there, but in physics, red plus green makes yellow. So light is different to paint pigments, strangely enough. And then we also have the rod photoreceptors. We have 100 million of those. And so they're sensitive in dim environments. They help us with our night vision. But in terms of just seeing how light or dark something is, helping with our white and black color too. But there are no subtypes for color. That's all they see. And so at nighttime, our night vision isn't great for color. We're good for seeing shapes and knowing how dim or bright things are. And that's about it. But lots and lots of very specialized cells allowing us to do this so that we have the wonderful sense that is sight. All right, so light is also important for vitamin D production. And so vitamin D is a common name given for calciferol, and its job is to promote calcium absorption in our gut, and it also moderates the calcium levels in your blood, because as the blood circulates around, it can go to your bones where it can then be taken in to mineralize your bones and strengthen them so they don't break. So obviously very important to have strong bones, but also those other factors that it behaves with. And so we actually need sunlight to produce vitamin D in our bodies. You can see the graphic there. So ultraviolet B radiation then reacts with the vitamin D precursor in our skin called 7-dehydrocholesterol. So that creates another chemical, which is then moved to the liver, combined with other chemicals, vitamin D2 and D3, before that process is finalized in the kidneys when we have active vitamin D, when it can then travel in the body and do its thing. So light literally stimulates the production of a very important chemical in our bodies. And when it doesn't happen, we can have all sorts of problems. One example being rickets. And so rickets is a result of bones not forming correctly due to a lack of vitamin D, and therefore a lack of the mineralization that the bones need. So not only will they be weaker, they'll also be misshapen as a result. And so this has been seen can have genetic issues, but people who've lived in regions with little sunlight in caves, those sorts of things, yeah, not a nice place to be. Right, so next one we look at for humans is our circadian rhythms. And so you might have heard of these, or you may have heard of melatonin, which is related to these two. But basically, our bodies have a regular rhythm, which have a day and night cycle, and that helps us to regulate our activities, helps us to sleep, and all the things that we want to do at specific times. And so in the morning, we're nice and cool from our overnight sleep in terms of body temperature. But as we wake up, we get those blood pressure spikes, melatonin secretion stops, and then we become more alert, we're more coordinated, we react better, we're stronger, blood pressure, all the things we need to do to move out and about. Whereas later at night, melatonin secretion starts. That helps our body to settle, to calm, relax, give us that deep sleep so that we can rest and repair over the night. And so over the course of the day, we have this circadian rhythm of melatonin here. And so on the left, you can see that at 2 p.m., not much is happening, but maybe 7 or 8 p.m., depends on the person. The pineal gland begins producing this melatonin in the evening. So it comes to very high levels, peaking in the middle of the night. And then as it comes to waking hours in the morning, that decreases again. So melatonin facilitates a lot of those rhythms that we have, so that we're more alert in the day and we can sleep well at night. And if these levels are wrong, that can give us all sorts of grief. So there's a disorder called seasonal affective disorder, which is linked to the number of hours of light in the day. So that can link to mental health, and it's can be caused by not enough light at the right times. And so particularly in the very northern or southern countries where they have periods of the year where they have much less light, that can be a thing, and it can actually be treated with light therapy by using special types of light which mimic the sun. But basically, melatonin levels are suppressed by light, and that's our link to light. And so you can see on this graphic here, we've got some relatively normal levels of melatonin. So at night time, they're rising highly, ready for sleep. But we can see that if you're exposed to bright light, particularly blue, melatonin levels stay down here at the baseline. They don't go up. So you don't get that melatonin production. So you're going to have poorer sleep quality as a result. And so that's why it's really important for us to avoid really bright light in the night hours, especially blue light, because our eyes are trained to think blue light, that's the sky, it's daytime, I don't need to sleep right now. So if we're looking at Facebook with its nice blue interface just before bed, that's going to be blocking the production of melatonin, and it's going to affect our sleep quality as a result. You might sleep for as long, but you won't sleep as well. So it's important to avoid light late at night. There are also software that you can use which blocks blue light on your devices. So Apple has their night shift. There's other software like Flux. I'm running it right now. My computer screen has much less blue showing as a result, so that hopefully I can get a good night's sleep tonight. And there are also things like glasses you can use. So this graphic is presumably advertising those light blocking glasses. You can see with that darker red, that's the melatonin production when that bright light is blocked with blue light filtering glasses. And so you still get some drop in melatonin, but it's much better, and that's going to help you with your sleep. All right, so light is important to humans, but it's not just important to us. God made light as part of his creation. He made it first, and it's linked to a range of other things as well. And so first and foremost, you might have heard of photosynthesis. That's how plants generate energy, very important for us. Also actually helps them to grow and develop along the way. And then obviously it regulates our seasons, so the rhythms of the earth itself. And then light pollution can be an issue in our environment as well. So photosynthesis is where nearly all of the available energy on Earth comes from. So nearly all of our energy comes from the sun in the form of light and other forms of electromagnetic radiation. And so this solar power is generated by the solar panels, which are plants. They take in the light, they take in carbon dioxide, and they use that to produce carbohydrates, sugars, food, and the oxygen for us to breathe as well. And so then as the herbivores eat those plants, that energy can then be passed up the food chain. And then the carnivores eat the herbivores. And then when I eat my steak, I'm getting energy from the sun through the plants and the moo cow that I'm eating that ate those plants as well. That energy is all passed up the food chain. But it all came from the sun in the form of light, transferred chemically as photosynthesis. And so photosynthesis is actually a very complex process. Those ins and outs that I mentioned before are the net result. But there's a very complicated series of light-dependent reactions in combination with the Calvin cycle too. And so this is a brief little graphic of the chloroplast. And so these are the parts that make plants green. They're a green little organelle inside the cells of plants. And this is where all the action happens. So basically, ADP becomes ATP. And so basically, it's an energy carrier. Adenosine diphosphate becomes an adenosine triphosphate. And that third phosphate can then be used to deliver energy where it needs to go. And then NADP and NADPH are used as a means of moving that energy around between the ADP and the ATP. And so the light-dependent reactions happen on the left-hand side in terms of refueling that ADP to become ATP. And then that ATP can be moved to where it needs to be in the body to deliver that energy so cells can do all the things that we need to do to survive and thrive. All right, so plant development, not only do they do photosynthesis to get their food, they actually rely on light to grow as well. Not only that, they rely on specific types of light. And so with the graphic here, you can see that by using LEDs or similar colored lights, we can actually stimulate specific types of growth in plants by using different colors. And so there's this real hope that indoor farming using controlled light can increase yields and be really efficient and all that sort of good stuff. And so the blues and the violets, they typically trigger the leafy green growth and root growth, whereas the yellows and the orange, they improve the nutrition and taste of fruits, whereas the reds trigger rhizome production, which are underground stems, and also flowering too. So depending on what type of plant you want or what stage of growth that plant is at, you can direct that to some degree by using colored light. Or out in nature, we just know that the sun is providing all sorts of different colored light, and that allows plants to have what they need to grow. So not only does it help to grow specific characteristics of the plant, it can actually direct the shape of the plant itself. So you're probably familiar with the idea that plants will grow towards light. They will grow towards the sun. And this is the means by which it happens. They are plant growth hormones called auxin. And so what they do is auxin is generated in parts of the plant which are most shaded. And so if the light source is directly above, the auxin is produced at the top to get lots of nice plant growth right at the top, and then it's evenly spread throughout the plant in terms of the sides. But if the light is to the side and the plant needs to chase that light source, as the auxin collects on the shady side, that's going to cause this imbalanced growth as a result. And so the plant will actually grow more in one direction than the other, allowing it to bend and in turn seek that light so it can get more light to get the energy that it needs from photosynthesis. And so it can actually shape plants in terms of the directionality of a light source through those hormones of growth in the plant. And then lastly, we have the seasons. And so we know that in summer and winter, it gets hotter and colder. We have more and less hours of sunlight, but it's also the type of light as well. And so this is, it's varied in different regions during different seasons. And this is to do with the tilting of the axis of the Earth. So we end up having more or less light at different times, and in turn, temperature will fluctuate as well. And so you can see here that at the equator, the light comes pretty much straight onto the sphere that is the Earth. And so we get light over a small area here. But at the top, that light's still coming directly from the side, but it becomes spread over a large area because it's not such a flush surface, it's more of a slanted surface. And so that light is spread out over a wider area, which means those larger areas receive less light, less concentrated light, if you will. And so this links in turn with the greenhouse effect. So the greenhouse effect is the idea that the sun's light and heat can be retained with absorption of greenhouse gases, reflecting back of our atmosphere, which acts to insulate the earth and heat it. And that's good because we'd freeze to death otherwise. We wouldn't get enough sunlight if we weren't able to retain that energy and heat in some way. But some is also reflected back into space as well. And so it's about getting that balance right. And so the Earth will actually tilt on its axis sideways up to 23.5 degrees at different times of year. And so combined with what I mentioned before, this results in much less or much more hours of light and heat as a result. And so I mentioned plant growth before, but plants are actually also able to detect the number of hours in a day that they experience light as well. And so there are a number of experiments showing how plants grow when they're exposed to light for 6 hours a day versus when they're exposed to light for 8 hours a day or 10 or 12. And not only that, do they measure the total number of light in a day, it's also about consistency too. And so a plant might grow really well if it's exposed to light to 8 hours for a day. But if it's exposed to light for 4 hours and then put in total darkness and then put in light again for 4 hours, so those same hours, but just broken up with some darkness in the middle, it will not experience the same growth. It needs to experience 8 continuous hours for it to grow in the same way. And so plants are very specifically attuned to the numbers of hours of sunlight, not just the total number, but when that happens. And that in turn has implications on planting and harvesting in terms of farming as well. And then I mentioned too, seasonal affective disorder as well, affected by the number of hours in the day as well. And of course, thinking back to what we learned about circadian rhythms and melatonin as well, the number of hours in the day of light, sunlight, are obviously going to have effects on our circadian rhythms as well, in terms of our alertness and our sleep quality as the year goes on. All right, and then lastly, there's also the idea of light pollution. So we know that light has these really large effects on nature. And so now as humans, with the development of electricity and artificial light, we're actually generating a lot more light in the environment than used to be there. So at nighttime, it used to be the stars, the moon, that's it. But now we have all sorts of artificial lighting, so we can do all the things that we like to do at night. And so it's just important for us to be mindful of light as a source of pollution, as a thing that shouldn't be there in terms of nature. And so that might be simple as designing lampposts that aren't just shining light all the everywhere for the sake of it, having some kind of shading so it's only shone down where it's needed. But it can also be us in our homes and as we go about our regular activities and just thinking, am I using more light than I need to, and what impact might that be having as well? So I've got a graphic here which shows different amounts of light pollution. So on the left, you have the inner city sky. You can't see much of anything. Even in suburban, you can't see a whole lot as well. But if you get out in the rural areas or even a really excellent dark sky site, you can see this huge array of stars that were always there, but were just covered up by this sheen of low-level light, reflecting into the atmosphere from human activities. And so bad news for sky gazers, but also bad news for animals. Because when you look at it from outer space, we see a lot of light. That's a huge amount of light that wouldn't otherwise be there. You just expect to see that darkness all around. That's bad news for our species. Because I'm a little turtle. If I'm looking for the moon reflecting on the waves so I can head out to sea after hatching my egg, if I'm seeing a light that's an artificial source, I might be heading in the wrong direction. That's just one simple example along with the plants as well. Alrighty, so there we have it. We've had a look at how the importance of light in scripture as the first creation, something that God identifies with himself and also his children too. We had a look at light has both particle and wave properties. It's a very strange and complex thing. And as a result, it has lots of strange and complex effects on us. As humans, we need it to see, we need it for our bones to develop correctly, we need it to manage our rhythms and help us to sleep well. And in nature too, it provides literally all of our energy and intermingles with the seasons too. So we need to be really mindful in terms of how we're using light and the amounts that we do use. So thank you once again for tuning in. I pray that you learned a lot about this and the nature of light. Appreciate you listening as always, and I'll see you next time. Thanks.